Newton's second law of motion. Newton's second law of motion states that when a net external force, sigma F, acts on an object of mass m, the acceleration a that results is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. The direction of the acceleration is the same as the direction of the net force. It's kind of a fancy way of saying that the acceleration of an object equals the net force applied to the object divided by the mass of the object. This is often rewritten as F equals m times a. The sigma symbol in front of the F implies a summation, or adding up of forces. It's there to remind us that the net force on an object is often a combination of several forces acting on it in different directions. Sometimes we rewrite sigma F as F net. As Newton's second law states, acceleration is directly proportional to the net force, so it requires a greater net force to cause a greater acceleration of an object of a given mass. And acceleration is inversely proportional to the mass, so given the same amount of net force, a less massive object will be accelerated more than a more massive object. And the direction of the acceleration vector will be in the same direction as the net force vector. When we introduced the idea of force, we saw that force is in the SI units of newtons. We can now see from this equation that since mass is in kilograms and acceleration is in meters per second squared, a newton is a kilogram times a meter per second squared. When dealing with forces and Newton's laws, we often draw free body diagrams, also called force diagrams, to see which forces are acting on an object. In a free body diagram, we start with our object that is being acted on, a book sitting on a desk, for example. Next, we draw all the forces acting on the object. We have the gravitational force acting downward on our book, and since it's sitting on a desk, we have a force from the desk acting upward on the book as well. Since the book is sitting still and not accelerating in either direction, these forces are balanced, which means they cancel each other out, adding together, and the net force on the book is 0. What if our book was in free fall? Free fall means that only the gravitational force is acting on the book. In this case, then, we have a non-zero net force. There's not another force to balance the gravitational force, so the book accelerates downward. The most important thing to remember when drawing free body diagrams is to only draw the forces acting upon your object. Do not draw forces that your object is exerting on something else. Only the forces acting on your object are contributing to its motion. Let's look at an example problem using Newton's second law. Two forces act on a 4.8 kilogram bowling ball at the same time. One force is 55 newtons to the east, and the other force is 45 newtons to the west. What's the acceleration of the bowling ball? Okay, so what are we given? We have a bowling ball with a mass of 4.8 kilograms. The bowling ball has some forces acting on it, so we'll draw a free body diagram for the bowling ball. But first, let's choose east to be to the right and to be the positive direction. The problem tells us that there's a force on the ball to the east with a magnitude of 55 newtons, and there's a force to the west of 45 newtons. Since the force to the east is in the positive direction, we'll give it a positive value. Since the force to the west is in the negative direction, we'll give it a negative value. Even though the problem doesn't mention vertical forces, we should always try to remember that in most cases the force of gravity is acting on our object. We'll draw the force of gravity downward, and then a balancing force working upward on the ball from the surface that it's rolling on. These two forces balance each other out so that there's no vertical motion, and we only need to worry about the east-west motion. Next, what is the problem asking for? The acceleration of the bowling ball. So now we need an equation. The equation for Newton's second law contains force, mass, and acceleration. That will include our knowns and unknown. We're looking for acceleration, so we want the form of the equation that solves for acceleration. Next, we need an expression for sigma F. Sigma F, the net force, is the summation of all the forces acting on the bowling ball. Since we know the vertical forces cancel each other out and we're only concerned with the horizontal forces, we'll say that sigma F equals Fe plus Fw. Now we can plug this expression into our equation for acceleration. And now all of our knowns and our unknown are written out explicitly in this equation. Now we can plug in the values that we know. And now we use our calculator to solve, getting a value of 2.1 meters per second squared for the acceleration of the bowling ball. And since the value is positive, the direction is east. Let's check to make sure our answer makes sense. The force in the east direction is greater in magnitude than the force in the west direction, so it does make sense that the acceleration of the ball would be in the east direction. It worked because we got our signs right when stating the values for our forces. When working these problems, be sure to be careful when assigning positive and negative values to your forces, and check your answer to make sure it makes sense.